So this is the outline of, okay, let me see. Okay, here it is. This is the outline of my talk. So I'm only going to briefly review this tremendous problem, astrophysical problem. But these mergers of binary neutron stars will be discussed in great detail during this long program at IPAM, especially during workshops 1 and workshop 3. There's a lot of suggested reading that you can do on this particular topic, and I have listed here a number of references. They are mainly reviews or books that, if you're interested in the topic, you can further consult. So this is the outline of my talk, why we care about studying binary neutron stars, and then mainly I will focus on the numerical aspects of this problem, how to simulate numerically using the tools of numerical relativity these collisions. So I will briefly touch on the Einstein field equations that you have already heard a lot during Helvi's tutorial. Then I'll briefly comment on initial data, and I will also discuss relativistic hydrodynamics and relativistic MHD. And towards the end of the talk, I will just present some examples of where the field more or less stands currently. So you've heard about binary neutron stars, so why do we care about studying these objects? So the neutron stars were theoretically postulated by people like Bade and Zwicky in the 30s of last century as the end results of supernova explosions. And it was not until the 60s, 1967, where the first neutron star was actually observed using radio astronomy. It was observed by Jocelyn Bell Burnell. And a pulsar, it was observed as a pulsar emitting radio pulses. A pulsar is essentially a rotating neutron star. So this is a very compact star, very rapidly rotating star, and with the largest magnetic fields that we know of. But the only evidence we have from up to September 14, 2015, the only experimental evidence we had about the existence of gravitational waves came from the study of these pulsars when they form binary systems, compact binary systems. And this was a system first observed by two radio astronomers as well, Russell Hulse and Joseph Taylor in 1974. This is the binary pulsar 1913 plus 16. And not only the observation, but also the interpretation of the decay of the orbital period of this particular object was the reason why they received the Nobel Prize in Physics in 1993. So this is an amazing object because the orbital evolution of this pulsar, of this binary pulsar, and of all binary pulsars for that matter, agree very well with that of a compact binary system that emits gravitational radiation according to our preferred theory of gravity, which is general relativity. So what you can see here in this plot, this is from a review paper by Bisberg and Taylor in 2004. What you can see here is the shift of the period of the pulsar as a function of time for several decades. You can see the numbers at the bottom. So what you see in red, these are the predictions of the experimental measurements of the period of this binary system. And then in blue, what you have in blue superposed on top of these red symbols, this is not a fit to the symbols actually, but is the actual prediction of general relativity, how the period of this particular binary pulsar will decrease if we believe that the system is emitting gravitational radiation, and that's why the period is being reduced and the orbit is shrinking. So one can see in this figure that the agreement is nothing short of spectacular. So it's really wonderful. So one can use the quadruple formula, the quadruple formalism, in order to study these binary pulsars in great detail. And one particular number that one can come up with is the so-called time to the final coalescence of the two objects. And this is an expression that is given by this formula here, where you have this prefactor, and then you have the speed of light to the power of 5, the Newton's constant of gravity to the power of 3, and then you have the initial separation between the two objects. This is L0 to the power of 4. Mu is the reduced mass of the system, and capital M is the total mass of the system. So if you plug in the numbers for this particular system, in the end, you see that the time up to the final coalescence is larger, is of the order of giga years, right? About more than 1,000 giga years, right? So this system will merge within the Hubble time, but still we have to wait for a very long time to see it happening. So more convincing or even more accurate results have been provided for other systems, in particular for J0737/3013, which is another binary pulsar. So until merger, these kind of systems are emitting a universal type of signal, which you all know. This is a distinctive chirp gravitational wave signal, which is the same type of signal for all coalescing quasi-circular binary systems. So this is like a sinusoid whose frequency and whose amplitude is increasing with time. So if you look at this frequency and time, the same figure here, the same kind of time series, but in the frequency time domain as a spectrogram, you can see that the frequency increases in time. These are the kind of signals that LIGO and Virgo are observing for compact binaries. Okay, so this is rather generic before merger, but after merger, the situation is quite different, as we will see in a minute. So in our galaxy, a number of compact binary neutron stars have been observed, at least 6 of them. I'm not sure if further binaries have already been detected, but I think this is pretty accurate. So you have the different systems here. This is obtained by the review by Lorimer, 2008. All of these systems will merge within a Hubble time. You have the names of the systems here on the left. You have some of the characteristic numbers for these systems, like the period in days, the eccentricity, the component masses in units of the solar mass, the total mass of the system, and the gravitational wave merger time. So this is the time of the merger in units of 10 to the 8 years. So you can see, for instance, that the Hales-Taylor pulsar is quite an eccentric binary system. So it's not rather quasi-circular system. It has a high eccentricity. However, this here 0737/3039 has an eccentricity of almost 0, and the last one also has an eccentricity of almost 0. So these are two perfect examples of quasi-circular systems. But in all of them, you can see that the gravitational wave time of the merger is very, very large. So by the way, this formula can be, these numbers can be obtained using this particular formula here, which gives the time as a function of the mass ratio of the system, the separation of the system, and the mass of one of the components in units of 1.4 solar masses. So if our detectors can only observe this kind of mergers within our galaxy, then the rate of events is extremely low, right? So we have to design experiments that can go much farther away, so that the rate number of events increases to detect a significant number of them and do astrophysics with them. So the Hales-Taylor pulsar was our first indirect evidence of the existence of gravitational waves, but we had a direct detection of gravitational waves in September 14, 2015, which was the first gravitational wave observation by LIGO, the LIGO-Virgo collaboration, but it was only observed by the two LIGO detectors. And this was the merger, the final cycles and the merger of a binary black hole system. And well, as you can see here, the pre-merger signal is again a chirp signal, and below you have the spectrogram that shows that the frequency increases in time. So here, the signal was interpreted as the collision of two black holes of these masses here, 36 and 29 solar masses, and the final black hole mass was 62 solar masses. So 3 solar masses roughly was emitted during the last time of the merger as gravitational waves. So, and this was awarded the Nobel Prize in Physics to three pioneers of the detection of gravitational waves, Weiss, Barish, and Kip Thorne. So again, one can study the parameters of this system of the first detection as a function of black hole separation, and it's interesting to use the very same formula I was giving you before for the coalescence time, which is a formula that can be trivially derived using the quadruple formula, and I teach this to my students in general relativity in the last course in physics in Valencia. So this formula wouldn't really function at the very late spiral close to the merger, but still you can use those numbers. And here you can see if you change the separation between the two orbits, between the two stars, the two black holes in this case, you can compute the frequency of the gravitational waves, the period, the time to coalescence, and the luminosity of the gravitational waves emitted in these units, in GS units, or in times of solar mass times c squared per cycle. So if the two black holes were separated a distance of 1 astronomical unit, then the time to coalescence would have been larger than the Hubble time. So clearly that sets constraints on how separated these two objects were. Now, if the separation is 10 to the 5 kilometers, the frequency is within the range of LISA observations, which is quite interesting. If the frequency shrinks to 10 to the 3 kilometers, the separation is 1,000 kilometers, then the frequency is about 90 hertz, which is starts to be within the LIGO-Virgo-Cagra sensitivity band. And if it shrinks to 550 kilometers, then the frequency increases to a little bit more than 200 hertz, and that's the last orbit. So the system wouldn't do a further orbit. So this is the time the system merges is roughly only 27 milliseconds. So that's the final period of the final plunge. Okay, so you could do those numbers for all detections actually by LIGO. So that was the first detection, but as you all know, there have been many detections of binary black holes and binary neutron stars, and also the hybrid system, the mixed system of black holes and neutron stars. So the LIGO-Virgo-Cagra collaboration have released about 3 catalogs already. 2 of them have been published, and 1 is have been submitted recently. And more than 50 detections have been observed. Mainly, most of those are for binary black holes, binary black hole mergers. So the first observation of a binary neutron star merger happened on the 17th of August 2017, shortly after the Virgo detector was put online for the final 3 weeks of the O2 run. And then this was the loudest signal observed. And you can see here in the spectrogram, the spectrogram is much longer. The duration of the signal is much longer within the sensitivity band of the detector is much longer than for binary black holes. So it was about 100 seconds within the sensitivity band of the detector, which starts at a frequency of about 20 hertz or something like that. So this was an amazing event. As you all know, there was a lot of follow-up observations in the electromagnetic spectrum of this source, and this particular source gave rise to the so-called multi-messenger, to the beginning of the multi-messenger astrophysics. So there's a lot of physics that we can study or we can infer from the analysis of the waveforms associated with binary neutron star mergers. So from the point of view of gravitational wave physics, binary neutron star mergers are among the strongest sources. Now, from the point of view of nuclear physics, they are a perfect laboratory to study the supranuclear equation of a state of dense matter. And this is a key to decipher the neutron star physics and the equation of a state. Also, the association between short, hard gamma ray bursts and binary neutron star mergers was something that had been postulated for a number of years, and this provides a clear association between gamma ray burst physics and neutron star mergers. In addition, from these mergers, one can study the so-called emission due to the radioactive decay of byproducts of the R process matter from material ejected in the merger, mainly neutrons, which are rapidly captured by the elements that surround the system. And this produces a very distinctive pattern of emission, of decay, radiative decay. So these systems are isotopes which are radioactive, and they are going to decay, but the rate of capture of neutrons is much faster than the rate of decay. So for a while, they are building more and more isotopes with larger, atomic number. And then after the neutrons have been captured, the decay starts, the radioactive decay starts, and this has a very particular profile that was, suggested some 10 years ago before the detection, or 20 years ago. And the maximum emission of this system is about 1,000 times larger than the typical emissions in a nova. In a nova, and 1,000 times or a few times, well, quite sometimes smaller than what happens in a supernova. So since the emission is 1,000 times larger than that of a nova, this system was dubbed kilonova, right? And then for cosmology, I mean, if we are able to detect the location of the source, we can infer the redshift, and this gives us a means to estimate the local value of the Hubble parameter, and then we can do cosmology with binary neutron stars as standard sirens. And then the funny thing is that most of these very, very important issues in relativistic astrophysics have essentially been established or supported by just one single multi-messenger observation with GW 170817, which is really an amazing result. So now in upcoming detections, in upcoming observing runs by the LBK, in 04 and 05, the number of BNS detections is expected to increase, and we hope that significantly increase. And therefore, it is very important to develop further phenomenological waveform templates for the inspiral phase. This is very important for the inspiral phase, and this can be done using approximations to general relativity. And there are many new ingredients that have to be incorporated to these phenomenological waveforms. Those are precessions, tides, higher modes, eccentric orbits, and so on. So this is extremely important. And this inspiral part of the signal, as you know, is very important in order to estimate the equation of state, the masses and the radii from the tidal deformability parameter. Okay, and a number of papers have already studied that for 170817. But equally important is to develop gravitational waveform templates for the merger and the post-merger phase. And there you cannot just do approximations to GR, because the size of the object is you cannot approximate the object as point particles. The final size of the object becomes important. And then one has to do fluid dynamics in curved spacetimes. So therefore, this is done using numerical relativity simulations. When the final post-merger object collapses to a black hole, then again you can do other options to simplify the study, like perturbation theory of black holes. But during the late part of the merger until the final formation of a black hole, then you don't have any other chance than doing numerical relativity simulations, solving Einstein's equations in a computer. Now, some of the answers that you expect to get is to know what is the end product of the merger, what are the oscillations modes of the neutron stars or of the hypermassive neutron star that forms after the merger, because that can provide you information through astroseismology studies that can provide information about the final temperature supernuclear equation of a state, and this is terribly important. Now here in this lecture, I will briefly review the current efforts on the numerical relativity front, and this constitutes a computational challenge and a physical challenge. So as I was saying before, the early part, before merger, this signal, this chirp-like signal is universal, and this can be studied using approximations to GR, like post-Newtonian approximations, or the effective one-body formalism. But from the late merger to the end, the final black hole, and you can use numerical relativity. So you have many issues to incorporate here, like Einstein's gravity, hydrodynamics MHD, magnetic field amplification, supranuclear matter equation of a state, neutrino emission, also nuclear reaction networks if you want to study the ejecta and the kilonova emission. So the modeling, I would say that the modeling of the post-merger waveform in numerical relativity is the current frontier. So most efforts are being spent in that particular part of the problem. Now, this is a sketch of what happens when two neutron stars collide, or when one neutron star and a black hole collide. So in some sense, this is a similar end result. So the end product essentially depends on the masses of the objects. So if the masses of the two neutron stars, the total mass of the system is sufficiently high, then you have directly prompt collapse to a black hole. And then if you look at the spectrum of the system, this is what you get. The frequency increases with time, and then there's just a sharp cutoff in the frequency, which is where when you have the black hole quasi-normal mode ringing here. Okay, this would be the late merger, and then this is the quasi-normal black hole ring down. So the frequency of this signal is very large. It's over 6 kilohertz. So it is impossible to actually detect these signals with current second generation detectors. Now, if the masses are not too high, then you have essentially three possibilities. So you can form a hypermassive star, neutron star, and this is what people believe is more common. In this case, the remnant is supported by two effects: by differential rotation, so the magnetic field is not too large and there is no magnetic braking, so the rotation is still differential, and also by thermal gradients. Okay? The time of collapse to a black hole is not very large in that case, about 10 milliseconds, but eventually it will collapse to a black hole because gravitational radiation is taking off angular momentum support of the system, right? Now, if the masses of the two neutron component masses are slightly smaller, a little bit smaller, the total mass is a little bit smaller, then you can form a supermassive neutron star. The total mass is small enough to be supported by rigid rotation, and we will have rigid rotation in the end due to magnetic braking, because the magnetic field will be amplified to very large values, and that will turn the differential rotation into uniform rotation. Then the time of collapse to a black hole in those systems is slightly larger, maybe 1 order of magnitude larger. And you could maybe, in some cases, even have a stable remnant, a neutron star which is stable for longer periods if the total mass is even smaller. So if you look at the power spectral density at the spectrum of the gravitational wave, in the case of the formation of hypermassive neutron stars or a supramassive neutron star, then you can see that it's very different to the kind of spectrum you observe in the case of a binary of prompt black hole formation. You find in particular these peaks in the spectrum at frequencies slightly too high to the current frequencies that we are able to detect with current LIGO and Virgo, but still they are not too extremely high. So maybe in the future, with further upgrades of the detectors, maybe we should be able to observe these signals. And these peaks here is what allows to do astroseismology of hypermassive neutron stars and infer physical properties of the system through the study of oscillation modes of these objects. Now, this is a challenging numerical problem, as I was saying, for many reasons. From the mathematical and the physical point of view, the system involves strong gravitational fields, involves matter motion with relativistic speeds. It also involves shock waves, contrary to the binary black hole case. So this is more complicated from that point of view. It involves strong magnetic fields, and it also involves nuclear physics, like equation of state, radiation transport, and networks, nuclear reaction networks for the kilonova, for the ejection. Numerically, it's also very challenging because it's a 3D problem. You have to do the simulation in full 3D. You have the complexities of Einstein's gravity, the formation of coordinate degrees of freedom, and the formation of curvature singularities, black hole formation as the evolution proceeds. And you must be able to capture, both the near zone in order to resolve the merger process itself, but also you have to be able to resolve the wave zone far from the source in order to be able to extract gravitational waves. So the spatial scales involved are also very large. And also computationally, you have lots of difficulties because it's a time-dependent problem and major resources are needed in terms of memory and in terms of CPU time. And also this parameter space, as you can imagine, is very large. So you have to do simulations using supercomputers. So the first simulations of binary neutron stars started with a seminal work by the Japanese group Shibata's group, Masaru Shibata's group, and collaborators Koji Uryu at the early 2000s, 2002 or so. So we have about 20 years, 2 decades of simulations of the binary neutron star mergers. And a lot of progress has been done in these last 2 decades. As you can see in this reference here by Luca Baiotti and Luciano Rezzola, this is a review paper where summarizes the state of the art of the field in 2017. So an example of what we are able to do currently is provided by this plot, which is the result of this so-called core collaboration. This is a computational relativity collaborations public database of gravitational waves from binary neutron star mergers. You can go to this website here in order to see this. So what you see here in this plot are different symbols with different colors. Each of the color corresponds to a different equation of a state. The equation of a state is plotted at the top. So you have here the most sophisticated and state-of-the-art equations of a state for supernuclear matter that are available in the literature. And then in the vertical axis, you see different simulations depending on the equation of a state, the total mass of the system, the mass ratio of the system, the spin of the system. This is the eccentricity of the system, the quadruple deformability parameter of the system, number of orbits that we are able to do, and the resolution of your simulations. So in total, this paper was published in 2018 by Dietrich and collaborators. And here there's 367 waveforms. So about 150 million CPU hours on supercomputers were spent in order to create this catalog. And this waveform catalog is essential. It's essential in order to validate LIGO-Virgo parameter estimation pipelines. Okay, so as I was telling you, the Inspiral Signal, this is another example from the same catalog for 6 different situations, like from top left to bottom right, we have equal mass system, high mass ratio, precessing systems, eccentric binary mergers, or including viscous hydrodynamics in the simulation. So in all of these figures, but the eccentric one, which corresponds to a hyperbolic encounter, so it's not a quasi-circular binary merger, in the rest 5 figures here, you can see that the Inspiral Signal, the chirp signal, is essentially the same, is universal. However, from the merger on, the merger is right at the maximum of the frequency, of the amplitude, and also of the frequency, of course. Right from the merger onwards, the post-merger signal is completely different. It depends a lot on the detail of the initial data, okay? And also depends on the equation of a state, even though here probably there's only one equation of a state involved. So it is very important to know how the waveform looks like in the post-merger part of the signal, which is the most different one, okay? All right, so the basic theoretical model that we use in order to do these simulations, to be able to perform these simulations, is based on two building blocks. One of them is the Einstein's field equations, which are written here in covariant form. So we have long-term stable formulations of those equations, both mathematically and numerically. One favor formulation is the so-called BSSM formulation, which is a strongly hyperbolic formulation. And then we have also suitable methods to solve the Einstein's field equations, like high-order finite differencing or pseudospectral methods for the initial data. And the second building block is the hydrodynamic equations, or MHD. So these are the conservation laws of the energy momentum tensor and of the density current. Again, we have long-term stable and conservative formulation, flux conservative formulations of those equations in GR. One favored one, again, is the so-called Valencia formulation that we put forward in 1997. And again, there are strong and solid methods in order to solve those equations, taking advantage of the fact that those are hyperbolic equations. And these are the so-called high-order shock-coupling finite volume schemes. So this is the current frontier, these 2 building blocks. So the current frontier is to be able to do initial data, more generic initial data, incorporating eccentric orbits, spins, and precession, Also improving the microphysics for thermal equations of states. So finite temperature equations of states are going to be very important in the post-merger phase. Magnetic fields are crucial in order to better constrain the lifetime of the post-merger remnant, because we know that the magnetic field is going to be amplified mainly by magnetorotational instability. But in order to resolve the magnetorotational instability, one has to use extremely high resolution, extremely high. So the amplification of the magnetic field is an issue.
You have a
non-ideal
question on Zoom.
Okay.
Yes. Can you hear me?
Yes.
Okay. So the question, you're mentioning initial data.
Yeah. I'll be discussing initial data a little bit later.
Can I ask a question as well? Since we stopped at here. What is the C4 formulation?
C4 is a variant of BSSN, which incorporates a constraint into the formulation. So Helvi didn't tell you about that one?
I don't remember it.
So it's a formulation. It's similar to what one does in MHD, when instead of working with the electric field and the magnetic field, one works with the electric field and the potential vector and the vector potential. Sorry. So you can. It turns out that you can do the same in the gravitational part. Okay. So it's you introduce a new field, which is similar to what you would do in the case of MHD, when if you use the vector potential formulation, similar to that approach. So it's being used, but I think it's not being used as much as BSSN, but it has improved stability properties in the wave zone because the boundary conditions are much more stable than these Sommerfeld boundary conditions that one applies to outgoing waves are much more stable than for BSSN. That's my understanding, but I am not really an expert on that particular formulation. Okay, so as you can see here, the current frontier is still a little bit difficult to investigate because most existing simulations employ cold equations of a state, piecewise polytropic equations of a state. Very, very few include thermal equations of a state or neutrino effects and MHD. Okay, and the approximation of the transport of neutrinos is done with simplifications to the Boltzmann equation. So even though we have done tremendous progress on the modeling of the post-merger signal, of the post-merger physics and dynamics, we're still quite far away of getting the final answer. So the thermal conditions of binary neutron stars in the post-merger phase are very, very important. In the inspiral phase, up to the late inspiral phase, neutron stars can be approximated by zero temperature polytropes, zero temperature equations of a state. So if neutron stars are sufficiently old, 10 to the 7 years old or so, they have undergone long-term cooling by both photons and neutrinos. So the temperature of those stars is of the order of 10 EVs. So that's much, much smaller than the Fermi energy, which for neutron stars is of the order of 100 MeV. So orders of magnitude larger, right? So for white dwarfs, this Fermi energy is of the order of 0.3 MeVs or something like that. So these neutron stars in the inspiral phase can be modeled by cold equations of a state. The problem is that such equation of a state is not known. So a systematic survey is necessary in order to study this. So the detection of 170817 was found that it favors soft equation of a state. The analysis of the tidal deformability parameter in the inspiral favors soft equation of a state. That means more compact neutron stars. However, during the merger phase, the story is completely different because in the merger phase, there is shock heating and neutron stars are hot. And the temperature increases to about 0.1 to 0.2 Fermi energy values. So this is about 10 MeV or something like that, maybe 50 MeV. Therefore, this cannot be approximated by a zero temperature equation of a state. And there are new effects likely to play an important dynamical role once we incorporate the effects of a finite temperature. So the neutron stars have to be modeled by thermal equations of a state, but again, the problem is that those equations of a state are very few. So necessary to do a systematic surveys of those equations of a state as well. So a major step forward in our ability to perform simulations of binary neutron star mergers without the issue of which equation of a state to use during the inspiral phase was provided by this paper in 2009 by Jocelyn Ritt and collaborators, who found that it is possible to fit essentially with a few parameters, essentially 3 parameters, 4 in some cases, but essentially 3 parameters, all the possible equations of a state, zero temperature equation of a state at supernuclear density matter. And here you have those parameters. So one of them is gamma 1, which is these are piecewise polytropes, what these authors use here. Gamma 1 would be the adiabatic exponent of the polytrope that goes all the way from the crust to the density of 10 to the 14.7 grams per cubic centimeter, which is the first point that they use in order to build the first polytrope. Then will come another polytrope, another piece, which is gamma 2, that goes from that density to this other density, 10 to the 15 grams per cubic centimeter. And then P1 is just the polytropic load, that is the pressure for the value of this density and the value of gamma 1, okay? And as you can see here on the right plot, the red curve here is just so these are different interpolations. All the curves here are different piecewise polytropic equations of a state to approximate called equations of a state available in the literature, including all kinds of effects, not only standard fermions, but also exotic particles like hyperons, mesons, pions, and even quarks, the confined quarks. So this was a major contribution to the community, because most people are currently using these piecewise polytropic equations of a state in order to do the simulation. And for the post-merger phase, the thermal contribution is taken care of using this gamma law fluid perfect fluid equation of a state within a given range for the adiabatic exponent. All right, so let me briefly mention about the 2 building blocks I was telling you about in order to do these simulations. One of them is Einstein's equations in 3+1 form. There are other formulations of Einstein's equations, but it's mainly the 3+1 approach, which most people use nowadays in the modeling of the systems. Because for the binary system, other approaches like the characteristic formulations are not very suitable for a number of technical details. So I'm not going to discuss the Einstein's equations, because you already discussed them in detail in Helgi Wittek's tutorial. You know that evolution equations and constraint equations can be obtained using appropriate projections of the Einstein's equations. If you do 2 normal projections onto the slides, onto the hypersurface, the spatial hypersurface, you obtain the Hamiltonian constraint equation, the energy constraint equation. If you have a mixed projection using 1 normal projection of the Einstein's equations plus a space-like projection within the hypersurface, you obtain the other constraint equations. This is the 3 momentum constraint equations. And within the hypersurface, if you do a spatial projection, you obtain the evolution equations for the extrinsic curvature. The extrinsic curvature is defined from an evolution equation, which is a definition for the time derivative of the metric within a given hypersurface. So this is the system that people derived. This is the ADM evolution equation, or 3+1 formulation, or Cauchy formulation of the Einstein's equations. The first 6 equations are the definition of the extrinsic curvature, and then the other 6 equations are the Einstein's equations proper. So the time derivative of the extrinsic curvature. So this is a Cauchy problem. So you have initial data for gamma and k at t equals 0, which are subject to the constraint equation, these 2 equations over here. The constraints, I mean, you have to specify the coordinates through two freely specifiable quantities, which are the lapse function and the shift vector, that gives you information about the, you know, how the coordinates move from one coordinate to the next, the lapse of proper time, and how the coordinates move actually within a coordinate, because the velocity of the coordinates doesn't have to coincide with the velocity of the linear observers. So there's going to be a shift, and this is controlled by the shift factor. Now, these equations are not hyperbolic, so they are prone to numerical instabilities, and it took a while in order to come up with a system that is actually strongly hyperbolic, which is this BSSN system that Baumgartner, Shapiro, Shibata, and Nakamura proposed, which is basically based on a conformal and traceless formulation of the Einstein's equation. So the metric is conformally transformed using this conformal factor 5, and introducing new variables in these gamma functions. In the end, you end up with a system which is slightly larger than the original ADM system, but is strongly hyperbolic, and it can be solved. It has nice stability properties, and it can be solved using standard finite differences with sufficiently high order. Okay, this is the conformal trustless formulation of Einstein's equations that you have already heard about in Helvig's lectures, or the BSSN equations after Baumgartner, Shapiro, Shibata, and Nakamura. So one very important issue for doing binary neutron star simulations is the initial data, how to set up initial data. And basically, in order to set up the initial data, one has to, for the Cauchy problem, one must find solutions for the constraints. So these are the constraints equations, which look the same in ADM or in BSSN. And here on the right-hand side, you have the matter terms. The matter terms are this rho and this Sj. Rho is essentially the double contraction of the stress energy tensor with the normal to the slice. This is the matter energy density of the system. And in the momentum equation, you have on the right-hand side this vector Sj, which is essentially the matter current. So is the projection, one normal projection and one spatial projection of the stress energy tensor. Okay, so one has to find solutions for this problem. And the first proposal to find those solutions, those initial data for the Cauchy problem, was suggested by Lishnerovich as early as 1944. He suggested to solve the constraint using a conformal decomposition of the three metric. There are other possibilities, but this is the idea, or this conformal decomposition of the constraints of the metric, sorry, is the most widespread approach to get initial data for the Cauchy problem. And the idea has been further developed along the years. And the most recent approaches, I would say, are those of Pfeiffer and York in the 90s, I think, where they use a method which has a funny name, but is what people use in order to build this initial data. This is the so-called extended conformal thin sandwich method, which is what people currently use in order to build initial data. This approach, this conformal decomposition of the three metric, can be used for any kind of initial data. But for the particular case of binary systems, special things can be applied, okay? Now, if one takes into account that different physical assumptions, one of them is gravitational radiation reaction. So in relativistic binary systems, we know that this reaction, gravitational radiation reaction, is what drives the inspiral motion to a merger. This is what will happen to the Holtz-Taylor binary pulsar. And this is what it has been happening in all the compact binary coalescence events that LIGO and Virgo have detected. Now, if these two bodies are sufficiently apart, these spiraling orbits can be approximated by closed orbits. We also know that the orbits will be more or less circular because gravitational radiation is very efficient in circularizing the orbit, okay? Therefore, in this approach, the initial data, the equations of motion, takes into account that the motion can be described by a sequence of closed circular orbits of different radii, okay? This is a physical assumption, and this can be translated into a geometrical assumption by imposing that the space-time is endowed with a particular type of symmetry, which is helical symmetry. Now, this helical symmetry is plotted here in this plot here, which is obtained from a paper by Corbulon, 2006. You have here this helical killing vector of your spacetime, which is this particular combination of the time killing vector and the azimuthal killing vector. The azimuthal killing vector is multiplied by the rigid rotation, the angular velocity of the system. So if we choose coordinates adapted to this helical symmetry, it turns out that all the fields that one has to set up are independent of the coordinates t and phi coordinates, okay? And furthermore, the fields are unchanged when they are rotated at a constant angular velocity in the azimuthal direction. Now, this symmetry is actually exact in a number of gravitational theories which do not have gravitational radiation. So in Newton's gravity, this symmetry is exact. I mean, the two-body problem in Newton's theory was solved by Kepler, and this is a trivial problem. Okay, there is no gravitational radiation. In post-Newtonian extensions of the Newtonian gravitational force, gravitational radiation enters beyond the second post-Newtonian order. So this post-Newtonian gravity up to second post-Newtonian order also satisfies exactly this helical symmetry. And another situation where this helical symmetry is exact is in a very, very particular case where the gravitational radiation degrees of freedoms are just canceled out. This is the so-called conformally flat condition, or the Heisenberg-Wilson-Matthews approximation to general relativity, which amounts to assume that the spatial metric is conformally related to the flat-Minkowski metric by this conformal factor psi. And it further assumes maximal slicing condition, the trace of the extrinsic curvature in a given hypersurface vanishes. This second condition just simplifies the form of the equation, but it's not fundamental, I would say. Now, imposing these two properties, the helical symmetry and the Heisenberg-Wilson-Matthews approximation, it can be shown in this paper by Corbulon and collaborators, it can be shown that it leads to 5 elliptic Poisson-like equations for the Laplace function, the shift vector, and the conformal factor. These are these equations that you can see here. These are 5 elliptic equations where the Nabla operator or the covariant derivative operator and the Laplacian operator have this funny hat, this funny bar. This is just to indicate that the derivatives are taken with respect to the flat metric and not to the curve metric. Okay, there is one hand.
Yes. So the question is, so when you have this helical killing vector, then the orbits of the killing vector are time-like near the center, but become space-like far away, which means that the character of the equations, when you impose this symmetry, changes from elliptic inside to hyperbolic at large distances. So how is this compatible with these equations? Can you just comment on this? What's the mechanism?
I'm not an expert on that, but my understanding is that the separation of the two stars is sufficiently small that this issue that you mentioned is actually never an issue. So this is just to say that I cannot really provide further insight into that.
Can I ask something?
Yeah. Question?
Just wanted to ask, when you started saying that we need to solve the constraint equations, you said it doesn't matter if we solve them in the ADM or in the BSSN, but we apply the conformal transformation. So is it okay if we solve for the extrinsic curvature and not for the trace-free part of it? Or are we going to apply?
So when you are solving for the initial data, you don't care about the evolution equation. So the constraint equations are those 4 elliptic equations that I just wrote here. So and they are.
But then the variables that we will have, they will all be conformally transformed. So if we solve those, how do we make sure that they will be applied through the whole time evolution? Are you applying?
The gammas and the Ks Oh, okay, because you do it for the conformally related metric and extrinsic curvature. Okay, you're right. Yeah. So in that case, if you were to do it with the BSSN equation, you should write the corresponding initial, constraints for gamma tilde ij and a tilde ij, which is the conformally related extrinsic curvature. You're right. Yeah. Yes. Okay. So how much time do I have, by the way?
About 25 minutes until the 75-minute mark.
Okay. All right. So these are the basic ideas about how to build initial data for binary neutron star mergers regarding the space-time part of the problem. Now, we also have to solve the equations for the fluid motion in addition to the Einstein constraints. And in order to obtain equations for the fluid motion, essentially, this amounts to solving the conservation law of the stress energy tensor in this context of helical symmetry that we were discussing before. Now, it can be shown that a first integral of motion can be found from this equation, from the conservation law of the stress energy tensor. A first integral of motion can be obtained in two cases, and this was shown by Gorgulon and collaborators in the 2000. So the first case is when the stars are co-rotating. This means that the fluid for velocity is collinear to the helical killing vector that we are imposing, and this would be something akin to assume rigid motion, uniform motion. Okay, and the second case is when the stars are rotational. So the vorticity of the system, the rotational, the rotation, the curl of the for velocity vanishes. Okay. Now, which one of the two options shall we choose for our simulation? So I guess that this depends essentially on the input that you may get from astrophysics. So from an astrophysical point of view, the second case, the rotational motion, is more interesting than the co-rotating case, because you should, in order for the system to co-rotate, you should ensure that the synchronization of the spins of the stars to the system's angular momentum. And this can also happen if the viscosity of the stars is sufficiently high. And for neutron stars, this is typically not the case. So the spins are actually quite low, so this rotational motion is particularly a very good approximation for slowly rotating stars. So this wouldn't be a valid approximation for millisecond pulsars, as the frequency of the spin of the individual components is much smaller than the orbital frequency at the late spiral. Therefore, one can safely neglect this. This is not to say that it is not important to account for spins in the component stars. It is important if your system is not quasi-circular. So if you have a hyperbolic encounter or a parabolic encounter in a situation where you can have high density of neutron stars which are not in a bound orbit. This may happen, for instance, in globular clusters or core clusters, neutron star clusters. Then you can have those hyperbolic encounters, and the spins of the individual components can be important in those cases. Okay, but for quasi-circular binaries, which is the most studied case and the most important case, the spin of the individual stars can be safely neglected. So this initial data can be built using different codes. One of them, probably the most used one, is the so-called Lorraine code, which is an open source multi-domain spectral method code to solve these elliptic equations of the initial data and generate these quasi-equilibrium binary configurations in quasi-circular orbits in general relativity. This is for all types of binaries, actually, not only neutron stars, but also black holes and the mixed system. Also exotic compact objects as well, like boson stars. And this is being used by most numerical relativity groups. And the good things about this package is that this initial data is available for piecewise polytropic equations of state and also for tabulated equations of state. And you can obtain also freely, they are freely available. You can obtain those equations of state from this from the composed collaboration, which is the result of a cost action in Europe, the so-called new CompStar action, and also from the Stellar Core Collapse website. You can get these equations of a state. And then this initial data can be used as input for numerical relativity codes. And we are in a very good situation nowadays because there are public domain open source codes which are state of the art for doing evolutions as well. One of those is the Einstein toolkit. There are more codes, but one of them is the Einstein tool that you can download from that website. And as I was saying before, you can also have initial data for binary neutron stars that includes the spins, and you can see details on those, on how to build those initial data in these references by the JENA group, Volkan Tiki and collaborators. Okay, so let me now move on to the second building block that I was mentioning, which is the hydrodynamics and MHD equations. So before going to the equations in full general relativity, it's worth to recap those equations in the case of classical fluid dynamics. So the Euler equations of fluid dynamics that you all know are the conservation laws of mass, momentum, and energy, and they can be cast as a nonlinear hyperbolic system of conservation laws, as written here in a very compact way. U is the state vector, which is the density, the momentum along a given direction, and the total energy, okay, including the internal energy plus the kinetic energy. Those would be the fluxes, and those would be the source terms, where in the source terms in general, if you don't have a gravitational field, for instance, or a conservative external force field, the source terms will be 0. But if you have a gravitational field that satisfies Poisson's equation here, so the gravitational field acceleration is computed from the gradient of a potential because it's a conservative field, and this potential satisfies Poisson's equation. Okay, those enter in the right-hand side of the fluid equation. Okay, so this would be the system similar to the Einstein plus hydro equations in GR, but this would be in the classical case. Now, this is a hyperbolic system, and hyperbolic systems have this finite propagation speed. The information can only travel at finite speed, and the maximum speed is at most that given by the largest characteristic curve of the system. And these characteristic curves are essentially obtained analyzing the wave structure of your system, and this is done analyzing the Jacobian matrices of the system. So in the case of classical fluid dynamics, these eigenvalues, these characteristic curves, are given by the speed of the fluid and this Galilean combination of the speed of the fluid and the sound speed. Okay? The same applies to the GR case, essentially, but only that the expressions are a little bit more complicated. Now, the equations are obtained from the conservation law of the current density and from the conservation law of the stress energy. So this equation here, the conservation law of the stress energy tensor, is an equation which is already included in Einstein's equations through the contracted Bianchi identities of the Riemann tensor. So the only equation that is actually new for the fluid part, for the matter part, is the continuity equation here on the left. Okay? So nabla mu is the covariant derivative associated with the 4-dimensional spacetime metric. J mu here is rho times u mu, is the current density, rho is the rest mass density, and u mu is the fluid for velocity. Now, this is in covariant form. You have to specify a coordinate chart in order to do numerics. And, well, you have to specify also an equation of state relating the pressure to fundamental thermodynamical quantities like a perfect fluid, a polytrope, tabulated equations of state, and so on. Now, if you can neglect the self-gravity of the fluid, the dynamics of the matter fields is just described by these two conservation laws. This is all you need. But if the self-gravity of the fluid is important, like in core collapse or in mergers of binary neutron stars, then those equations have to be solved jointly with Einstein's equations for the gravitational field. And this is the system that you have to solve. Okay, and the Newtonian analogy is Euler's equations of fluid dynamics plus Poisson's equation. All right? Okay, so you need to introduce a coordinate chart in order to write the equations as partial differential equations that you can discretize and solve. And by doing that, immediately you transform these covariant derivatives into, these partial differential operators, and then you introduce the connection coefficients associated to the one affine metric Levi-Civita connection symbol, and therefore you get these connection coefficients here on the right-hand side. What that these expressions, when expanded in terms of coordinates, have many terms. Okay, now one has to come up with a formulation that is actually flux conservative and hyperbolic, as in the case of the classical fluid dynamic equations, classical Euler equations, because this system, in the end, in the right limit, has to transform into the classical Euler equations in the Newtonian limit. And there have been a number of conservative formulations proposed along the years. So the first study was done by Jim Wilson, who wrote those equations as a set of advection equations, which is very nice, it's easy to solve, but that approach breaks down the conservation properties of the equations, and conservative formulations were proposed later. And the one I'm discussing here is this one here, Binocular et al. 1997, which is in 3+1 and is adapted and is valid for general equations of a state. And this is the formulation that nowadays people, most numerical relativity groups use nowadays, and it's called the Valencia Formulation. And this is the system. This is the hyperbolic system. So the state vector U now is a little bit more complicated. It has these three fields. These are 5 equations because one of them is the momentum along the direction xj. So we have the relativistic density, the relativistic momentum, and the relativistic total energy. Okay, so this tau would be the contraction of the stress energy tensor twice, the projection of the stress energy tensor twice with the normal to the slide. Okay, and we subtract here the first equation in order to recover the Newtonian limit. Actually, if you don't subtract the first equation, you cannot recover the Newtonian limit. Now you can see that those equations, this state vector is much more complicated than the state vector that you have for the Euler equation. So in the case of Euler equations, you have rho Vj, rho the momentum and the total energy. This is very simple, and you can go from these expressions. You can recover the velocity or the rest mass density or the pressure using an equation of a state. So everything is in closed form. However, in the relativistic case, those expressions are more complicated, and it turns out that it's impossible to obtain these so-called primitive quantities, the density, the tree velocity, and the specific internal energy, in closed form analytically from the state vector. And those primitive variables are used everywhere in your numerical code because they appear in the solution procedure, in the characteristic fields, in the sound speed, everywhere. So one has to use some kind of implicit iterative methods, root finding procedures, to go from one system of variables to the other system. And this is a special feature of the relativistic equation. Okay, so this is how the system looks like in general relativity compared to how the system looks like in Newtonian gravity, Newtonian physics. A good exercise for students is to try to derive the Newtonian limit of the equations by taking the appropriate limits. And this is something that you could try to do as an exercise if you haven't done it yet. All right. So, but as I was saying before, neutrons still have a strong magnetic field. So the current frontier of these BNS simulations, BNS merger simulations, also incorporate magnetic fields. Then we have to incorporate the GRMHD also into the business. So we have to study the dynamics of electrically conducting fluids in the presence of magnetic field. We typically use this ideal GRMHD situation where we neglect viscosity effects and heat conduction. We assume that the conductivity of the fluid is infinite. Our fluid is a perfect conductor. We know that that is not the case, but for neutron star matter, this is maybe not a very bad assumption. Now, the main difference comes from the fact that the stress energy tensor now includes the contribution for the perfect fluid part that I was discussing before, and from the electromagnetic part, the magnetic field measured by an observer which is moving with the fluid. So this is the form of the perfect fluid, the stress energy tensor that you all know. And this is the form of the energy moment of the electromagnetic stress energy tensor that is obtained from the Faraday tensor, okay, from the magnetic field tensor. Now, this Faraday tensor can be computed through this contraction with the Levi-Civita tensor, with the antisymmetric tensor for velocity of the fluid and the comoving magnetic field. And you can end up with this expression here for the stress energy tensor of the magnetic field with these definitions here. This can be simplified in the case of this ideal MHD condition, because the current is given by this expression here below. But if you take sigma infinity, if you assume that the conductivity of your fluid is infinite, then in order to keep this expression finite, the current finite, this quantity here, F mu nu contracted with the for velocity of the fluid, has to be 0 in order to keep the current finite. And that simplifies the final form of the stress energy tensor of the magnetic field part. So again, taking now the conservation laws of this extended form of the stress energy tensor, one can obtain this final first order plus conservative hyperbolic system. One of the equations is the conservation of mass. The other one is the conservation of energy and momentum for the extended form of the energy momentum tensor. And then the other equations are Maxwell's equation, essentially. So the covariant derivative of the dual of the Faraday tensor have to be 0, where the dual of the Faraday tensor is given by this expression here. And if you expand this system here, you end up with a constraint, which is the solenoidal condition. The divergence of the magnetic field has to be 0. And the other equation is the induction equation, okay, here. In the end, your system, your final system, is given by this expression here. U is the state vector that now, instead of 5 equations, you have 5 components, you have 8 components, actually, because you have 3 extra components due to the magnetic field contribution. And the expressions for the densities of relativistic densities of mass, momentum, and energy are slightly more complicated due to the presence of the magnetic field. And in addition to the hyperbolic part, you have a divergence equation, you have a constraint that has to be satisfied at all times, which is also similar to what happens in the gravitational field case, where you have the Hamiltonian and momentum constraint. Okay, the system is actually simpler to solve because you have much less equations and constraints than in the gravitational field case.
Question on Zoom.
Yes, there is a question.
Yes, so you have this formula for star F mu nu. This looks pretty much like an ansatz. Is there a mechanism which says that this is conserved, that this form of F mu nu is conserved, or you end up solving approximate equations?
Well, it is not. No, this is an exact expression, because this magnetic field, this is not the comoving magnetic field. This is the magnetic field measured by an Eulerian observer. And if you take the dual of this quantity here, well, of the Faraday tensor for an Eulerian observer, it can be shown that it can be written in this particular form.
So this is conserved by the.
And this is conserved by definition. Yeah.
Thank you very much.
If you want details, you please go to this reference. Everything is really explained there. Yeah.
Okay, thank you.
You're welcome. Okay, so how do we solve those systems of equations that I was just mentioning, and how do we do these binary neutron star merger simulations? So for the initial data, we have elliptic equations of this form. This is an elliptic system, and usually these elliptic systems are solved using a spectral method, so approximating the solution with a sum of functions with respect to a basis functions, typically Fourier, Fourier in the Fourier domain. So this is what Lorentz does. And for the evolution system, we have a hyperbolic system, both for the hydro equations of an MHD equation and also for the space-time metric for this in this BSSM formulation. Now, the metric evolution equations are usually solved by most groups using standard finite differences to approximate the derivatives, but very high order finite differences, up to 6th or 8th order accurate finite difference. This is done for the space derivatives only, okay? And the hydro MHD evolution equations are usually solved using finite volume schemes, these so-called high-resolution shock capturing schemes based on Riemann solvers. And for those, this is because they have shocks. The metric evolution equations do not have shocks, but the hydro evolution equations do have shocks. And therefore, we have to use a method that is able to capture those shocks. And this is done using these Riemann solver or Godunov type methods, DVD methods. And for those methods, the way, yes? 5 minutes? 5 minutes, okay. So the wafer structure is important in order to build this Riemann solver. Also, let me mention that for the time derivatives of the evolution system, we use typically the so-called method of lines, where the equations are cast in a compact way as a semi-discrete system, where we have that on the left-hand side of the equation, we have the time derivative of the state vector, and on the right-hand side, we have the remaining term in the evolution equations. And these terms here on this S also include spatial derivatives. So this is a way of disguising the partial differential equations as an ordinary differential equation. Okay, and therefore standard ordinary differential equation integrators can be applied. And typically, most numerical relativity groups employ third-order Runge-Kutta conservative Runge-Kutta schemes in order to solve those semi-discrete systems. Those were actually developed at IPAM in 1988. Okay, so I'm not going to discuss the wafer structure of the Hydro equations and the MHD equations because I'm running out of time. But let me just describe briefly in these 5 minutes that I have some examples of the kind of simulations that we can do nowadays. So this is the typical result of a simulation. So we have the binary neutron star merger. We have a hypermassive neutron star at some point. The lifetime of the hypermassive neutron star depends on the particular physics that we use as an input, but the end result is typically a black hole in the middle surrounded by a thick disk or torus. Okay, so variations on this general trend can be produced if you use differences in the mass for the same equation of a state and differences in the equation of a state for the same total mass. Okay, but this is the general trend essentially. Now, for the inspiral part of the signal, we can get information on the physics by analyzing the tidal deformability parameter of the system. And this is something that was shown in this paper by Jocelyn Red again and collaborators in 2013, where a systematic study of different cold equations of a state and different codes was done. And you can see here in this plot here, which shows the strain as a function of time. You can see that many different simulations, you have here the simulations, many different simulations have been overlapped at the time of merger in order to account for the possible phase difference, okay? And here you have the spectrogram on the bottom panel, okay? Now, if you plot, Red and collaborators found that if you plot the frequency of the gravitational waves at the peak amplitude as a function of the so-called tidal deformability parameter, which is this capital lambda, which is related to the quadruple Love number and the radius and mass of the star to the power of 5. If you plot the peak frequency of the gravitational waves as a function of lambda to the power of 1/5, you can see, you can fit the numerical data very well with this particular expression here, phenomenological fit here, empirical fit. So there's actually a universal relation between the frequency of the merger and the tidal deformability parameter. And this is a spectacular result. This has been extended also for tabulated equations of the state at 0 temperature. And this is what is allowing the LBK to infer properties on the equation of a state from the study of this tidal deformability parameter. This was already applied for 170817. This is an example for the highest spin case and for the lowest spin case. What I'm plotting here, this is from the LBC paper. What I'm plotting here is the tidal deformability parameters of the two stars for highest spin case and lowest spin case, as I was saying, and these are credible confidence intervals, the 50% confidence interval and the 90% confidence interval, and different equations of a state. And you can see that some of the equations of a state, like MS1B or MS1, are actually outside the 90% confidence interval, so they are ruled out. This kind of less compact neutron stars that are produced by these equations of a state are ruled out by this single observation of a binary neutron star merger event by LIGO and Virgo. Now, the post-merger signal is completely different. I was telling you before about these peaks that appear in the frequency spectrum. This is also universal. It has been shown in all simulations of the post-merger evolution, these peaks. And these are QPOs associated with particular modes of oscillations of the star. Okay, the frequencies are a little high, 2 kilohertz, 3 kilohertz. So they are still difficult to be detected by current detectors, but for 3rd-generation detectors, this may be detected. Okay, this may be within the capabilities.
About a minute
And
left.
I should be finishing?
Finishing, yeah, shortly.
Okay. So let me just tell you that these modes have been studied in detail by a number of authors, and they have found association between these frequencies of the oscillation of the stars with particular modes that are triggered during the oscillation. So you have the different physical effects drive different modes of oscillations. Like if you have pressure gradients, you have P modes or the fundamental mode. If you have rotation or Coriolis force drives another type of oscillations. If you have thermal gradients, you have inertial modes and so on and so forth. So this is very important because the analysis of this kind of structures in the post-merger phase can give you information on the thermal and rotational properties of the hypermassive neutron star. And in turn, if you are able to build a model, you can infer properties of the equation of state at finite temperature. So this is very important for the future of gravitational wave astronomy. And since I am running out of time, I have to skip all of these results that I wanted to show, but unfortunately I didn't have time. I'm sorry for running out of time, but I tried my best to give an overview of the numerical aspects that one has to really take into account in the modeling in order to be able to do those simulations. We are actually pushing forward the state of the art of those simulations by incorporating many, many effects. And all of those effects and all of those simulations and many things, many aspects of this problem related to mergers of binary neutron stars will be discussed in detail during this program at IPAM. And let me remind you that most of those topics will be discussed in the numerical relativity session or workshop, which is the first one, and in the parameter estimation workshop, which is the third workshop during the program. So thank you very much, and I apologize for having taken a little bit more time than allocated.